So let's take a closer look at the separation of forces with energy. And let's relate the energy also to the temperature in the universe at various times right after the beginning. Since temperature is a measure of the average energy per particle, we can translate the energies we've observed where the forces behave differently into distinct temperatures. Now, we have never been able to achieve a temperature higher than about 10 to the 16 Kelvin. That's 10,000 trillion Kelvin in a particle accelerator. So we have never been able to observe force unification better than just the unification of the electromagnetic and the weak forces that happens at about 10 to the 15 Kelvin, or 1,000 trillion Kelvin. But when we extrapolate the trends, we believe that the strong force united with the electroweak force at 10 to the 27 Kelvin, and that gravity was also comparable in strength to the gut force at about 10 to the 32 Kelvin. Before that, we have no idea what was going on. We need some kind of theory that unifies quantum mechanics and general relativity's description of gravity, and we don't have that. It is labeled at the top of this graph here as the quantum gravity era, before 10 to the minus 43 of a second, when the temperature in the universe was hotter than 10 to the 32 Kelvin. As the universe expanded and cooled, then gravity became weaker compared to the grand unified theory force that would be the unification of strong and electroweak. Then, at about 10 to the minus 34, at the soonest 10 to the minus 35 of a second after creation, the universe had cooled to 10 to the 27th Kelvin, and the strong force separated out from the gut. The strong force and the electroweak forces became distinct. The release of the strongest force in nature to act as its own would have released a tremendous amount of energy into the universe. And it is reasonable to speculate that perhaps that tremendous energy release would have inflated the size of space an extraordinary degree just at that very instant. We call that the inflationary epoch. The idea of inflation is that space suddenly became stretched an extraordinary degree by a number of times so high we don't even have a name for it. 10 to the 40th, 10 to the 50th, even 10 to the 60th or more times in just the briefest instant. And so all of space would have become rapidly much more stretched out, and the portion of space that is our observable universe today would have been even smaller at the beginning of the universe than the conventional Big Bang model would have said. Take a look at this graph here, the expansion of the observable universe. In this case, what we're talking about is the size of the portion of the universe that we can now observe today. If we extrapolate back into the past, how big, a radius in meters, was that portion of the universe that today extends billions of light years all around us that we can see? In the standard Big Bang model, it was very small right at the beginning. But in the inflationary model, it was incredibly teensy-weensy, and then suddenly increased in size by about 10 to the 50th fold when the universe was around, 10 to the minus 34 of a second old. Huge expansion in an incredibly short time. I remind you that the last graph was only showing the observable portion of the universe, that is, the amount that is observable to us. The universe will have extended far beyond that. Again, the universe may in fact be infinite, but if it is finite, it is still much larger than what we can see today. Our portion of the universe would have been, perhaps 10 to the minus 44 of a meter wide before inflation, and will have swelled to perhaps 1 meter wide after inflation. Other portions of the universe would also have inflated equally. There is vastly more to the universe than what we can observe. And just keep that distinction between observable portion of the universe and an imagined much larger whole in mind when we talk about specific numbers when we speak of the universe size inflating. While inflation is a speculative idea because it involves physics at temperatures far too hot for us to study, it solves three puzzles that the standard Big Bang theory could not answer. One puzzle was why the overall shape of space came out so nearly flat. Remember that required a critical amount of stuff in the universe, a certain critical density to happen. If the universe had more matter and energy than a certain amount, it should wrap around itself with a spherical-like geometry. If less, it should have been saddle-shaped. Instead, it came out exactly right to be flat, and standard Big Bang could not explain that. A second puzzle had been exactly why the cosmic microwave background would be the same 2.725 Kelvin to high precision in every direction. The standard Big Bang model actually does not explain why the temperature would be the same everywhere in the universe. A third thing that the standard Big Bang had no explanation for is the origin of structure. Our universe did not begin perfectly smooth, and if it did, we would not be here. Tiny little irregularities grew over time into the clusters of galaxies that exist in the universe today. Where did these structures come from? There would be no reason for the earliest universe to be completely without structure. The quantum foam was a roiling mass of energy fluctuations that would have produced regions of higher density and lower density. But we also would not have expected the early universe to have a flat space either. There could have been curvature in all directions and all kinds of fanciful shapes, as in this illustration here with the quantum fluctuations imprinted in an imagined space that is just full of bumps and curves and goodness knows what else. This is the imagined universe before inflation happened. But a sudden, really dramatic inflation of all space would smooth everything out. If you can imagine some structure in the universe actually hanging together against the super rapid inflation, like the ant in this picture, if we inflate the balloon to an extraordinarily much larger size, almost instantly, then the ant has gone from perceiving itself to be in a universe that could be highly curved to perceiving its immediate surroundings as being very nearly flat. The illusion is rather similar to the one that early people faced when they were wondering whether the earth was curved or flat. If you can only see so far around you, things look pretty flat.